So, what exactly is an enzyme? An enzyme is a biological catalyst. Um, they increase the rate of a reaction by lowering the activation energy. And this activation energy is the amount of energy that must be put in order for bonds to break and form in the substrate. Enzymes can be either catabolic or anabolic, and they can also perform some chemical reactions in both directions. So that could be the forward or the reverse reaction. So, enzymes are specific. This is a super important point. Many times you'll hear of the lock and key model, which I will get into in just a moment. But first, it's important to remember that enzymes are proteins with tertiary and quaternary structures. They are uniquely shaped, and they have like a little area, almost like a pocket, on their surface called the active site. So let me go ahead and draw out an enzyme. So let's draw it out like this. So this structure itself is the enzyme. Okay. And then that little area, the little pocket, that would be the active site. And this is where the substrates will bind. So you'll have your little substrate here. Whoops. And that will end up going right in here. So in the end, you'll have this, which as you can see is a lock, like a lock and key model. So far we have the enzyme itself, we have the substrate here, and then the active site here. But there is another part on the enzyme that we need to cover. So there's another site which is referred to as the allosteric site. So let me go ahead and draw. Let's use the same model that I had before, but I'll just incorporate the little allosteric site. So once again, this is our active site, this is the enzyme itself, and this is what we're going to call our allosteric site. So this can either be inhibitory or it can activate the enzyme. So let me further explain. Let's first start off with inhibition. So I'll go ahead and draw out an enzyme. Okay, so this is our enzyme. This is going to be our allosteric site. And then we have a little inhibitor here, which would fit right into this little allosteric site, right? Okay. And then, of course, this is our active site. So let me move this down. Okay, so say that our inhibitor ends up going into that enzyme. It fills that lock and key model. Let me draw that out. If that happens, that's going to change our enzyme completely. We're not going to have that same shape. It is changing the shape of our enzyme because it's inhibiting. So now our substrate that was supposed to fit in to our active site originally, it no longer has a place here. That substrate cannot fit into that enzyme because our inhibitor prevented that from happening. So let's reverse the role here. say we have an activator now. So we'll go ahead and use, let me draw another enzyme. So this will be our activation. And here is our activator. So say that this activator comes into play here, right? It fits into like a lock and key. And then once again, here would be where our active site would be, but in this case, our active site doesn't exist. By having our activator come into position here, that is going to create an area, the pocket where we can have our substrate bind. And that would end up looking like this. So here we have our activator filled in. And then our substrate is going to fit directly in here. So here we could see the difference between allosteric inhibition, which does not allow for our substrate to bind here. And then we also have our allosteric activation, where the substrate will only bind if we have this activator in place. Now, to complicate things a little more, I want to go ahead and talk about another type of inhibitor. So we've covered the allosteric inhibitor, but we also have the competitive inhibitor. And it's really important to know the difference between these two different competitive types of inhibitors. So competitive inhibitors will bind to the enzyme active site itself. And if you'll remember, with our allosteric inhibitor, our activator here never bound to the active site. It only would bind to the allosteric site. So allosteric inhibitor will only bind to the allosteric site. And then competitive inhibitor, that will be what binds to the active site. So let me go ahead and draw out an example here. So I'm just going to draw out a regular enzyme, right? And then here we would have our substrate. So this is the substrate that would bind here into our enzyme. All right, so moving over. Let me go ahead and draw out that same enzyme. Okay. So now if we have a competitive inhibitor, that is going to prevent our substrate from binding. It's essentially blocking that substrate from binding. So this shape that we have right here, it's no longer going to be able to fit over here. And that is because our competitive inhibitor, let me go ahead and change this pencil color. This would be our competitive inhibitor. So this shape over here, our original substrate, can no longer come in over here because this competitive inhibitor is in the way. So it's not going to fit in. And then with our allosteric inhibitor, just so I can show you the difference side by side, let me go ahead and draw out this enzyme. Okay. And then with our allosteric inhibitor, that would come in here to our allosteric site. So we'll have that filled. And then once that inhibitor binds to this allosteric site, that is going to change the shape of our enzyme. So now we are no longer able to have anything bind to our enzyme here. There's no longer a place for our substrate to bind. There's no active site for our substrate to bind to. So it's very important to remember that with an allosteric inhibitor, once the inhibitor binds to the allosteric site, that's going to cause a change in the shape of the active site, preventing the substrate from binding. This will technically slow down and may even stop the reaction from occurring. And then with our competitive inhibitor, once again, this is a molecule that can bind to the active site, and it's blocking our substrate from binding. And this will also slow or stop the reaction from happening. So both inhibitors do the same thing. It's just important to know the difference here. Okay, so we've covered how inhibitors can influence enzyme activity, but there are still other factors that will influence enzyme activity. Just to list them, these factors include temp, pH, substrate concentration, and also osmolarity. Okay, so first let's go ahead and talk about temperature. So temperature can help increase the rate of a reaction, but only up until a certain point. So let's go ahead and I'm going to draw a graph here. So this here is going to be enzymatic activity. And our temperature is going to be here. Okay, so as our temperature increases, we're going to see that enzyme activity also increases. However, it'll end up hitting a certain point, and once it hits that particular point, the enzyme activity is gonna fall dramatically. And once it hits that point, the enzyme becomes denatured due to the high heat, and it's essentially inactivated. So at that point, the temperature isn't really helping us. The enzyme is being denatured. So I also want to add that with temperature, there is an optimum temperature, which would be where enzyme activity is the highest. So here, that would be our optimum temperature. And below the optimum, let me just note this. So anything below the optimum, obviously we can see that our enzyme activity is low. The molecules are moving more slowly. And the slower the molecules move, the slower the rate of enzyme activity is. And then above optimum temperature, we can see that the enzyme becomes distorted, and that also slows the rate of enzyme activity. So now let's go ahead and talk about pH. We're kind of going to see the same thing that we saw with temperature. So again, I'm just going to draw a graph here. And again, this is going to be enzyme activity. And this here is going to be our pH. So our graph will typically look like this. And then, of course, we're going to have an optimum pH. And this is going to be our optimum. And same goes. So the further away you get from the optimal pH, the more the enzyme is going to be distorted or denatured, or it's going to slow down the rate of the reaction. So that goes for whether the pH is going to be lower or even higher. All right, so now let's go ahead and discuss substrate concentration. And let's talk about how that influences our enzyme activity. So once again, I'm just going to draw a graph. This is going to be our reaction rate. And then here is going to be our substrate concentration. So remember, our substrate is what binds to our active site. It's the key to our lock and key model. So the more substrate you have, the faster the rate of the enzyme activity, is going to be. However, that is only true up until a certain point, which is the point of saturation. So as substrate concentration increases, so does the rate of our reaction, and then we'll hit our point of saturation. So what exactly is the point of saturation? That is when the substrate concentration is in equilibrium with the enzyme concentration. At that point, the reaction has hit its highest point, it's at its maximum. And if you add more substrate, it's not going to increase the rate further. It's going to stay at that same point. All right, and now let's go ahead and talk about how osmolarity affects enzymatic activity. So if you have extremely high osmolarity, that means you're going to have high solutes and high salts. That is absolutely going to affect the enzyme activity. So here you have regular cells, right? They're surrounded by just a normal solution. And then over here, this is our solution. And kind of these are our cells. And I'll explain why right now. So, if you have a hypertonic environment, right? So, this area here, that is more concentrated, right, outside of the cell. So this is highly concentrated solution outside of the cells. Well, that is going to affect the cytoplasm. That is dehydrating the cytoplasm. That's due to the water loss by osmosis. So our enzymes are going to dissolve into the cytoplasm, and then the excessive water loss is going to make the enzymes precipitate out of the solution. So you're going to end up with shriveled cells, as you see here. And that absolutely is disrupting our enzyme activity. It's disrupting the structure of our enzymes, and that is affecting the activity and how our enzymes work.